Welcome back to the second talk of this morning session. Our next speaker will be Robert Sims from the University of Arizona at Tucson, and he will speak about Lieb-Robinson bounds for quantum spin systems.
Okay, thank you very much. I'd like to begin by thanking the organizers for inviting me to this school. Okay, mood lighting, good. It's very nice to come to a cooler place. Tucson is a bit warmer than it is here. And I think I should begin by letting people know that I was raised as an analyst. So if the talk here seems a bit different from the previous talk, that could be how I was raised. But what I want to talk about today are Lieb-Robinson bounds. So Lieb-Robinson bounds have found many recent applications, and they all concern looking at a dynamics on one of these quantum spin systems. Yes, I'm not forward. Is that better? Better? Okay, good. So I was generally talking about quantum spin systems and Lieb-Robinson bounds. Lieb-Robinson bounds are a technique to measure the extent to which a given dynamics in a quantum spin system, which is a non-relativistic system, to describe the extent to which that dynamics is local. And so again, what I want to do is give a little bit of an introduction to quantum spin systems. Now, Daniel did a wonderful job starting this discussion, and I will talk a little bit more about it. I will come more from the perspective of quantum statistical mechanics. So typically when I look at an infinite volume system, it's a limit from finite volume systems, but that's a difference in perspective. I'll talk a bit about some models, what the Lieb-Robinson bound is, some words on the proof, and then two applications which will come up often in subsequent lectures. Okay? So let's start with quantum spin systems, and again, this will be a review of many of the things we talked about this morning. So the basic structure, again, is there's going to be an underlying countable metric space. I will call it gamma D. The extent to which it's embeddable in RD is not terribly important to me. It's just a metric space with countably many points on it, and each point has a distance from every other given by the metric D. In almost all the examples that we think about that are physical, gamma is Z nu, so some lattice that is nu dimensional, but that's not important in most of the results that I'm going to talk about. What are we going to do? Well, to each site x in gamma, we're going to have a finite dimensional Hilbert space of states, and the corresponding algebra of observables, the bounded linear operators over this Hilbert space, is going to be just the nx by nx matrices over C. So again, just as we saw this morning, I'm going to be looking at a quantum spin system. At every site, there's a finitely many degrees of freedom and a collection of observables. Now for me, the observables will be all bounded linear operators over the Hilbert space, so all matrices. An interesting observation is that the dimension of the single site Hilbert space, which here I've called nx, is often related to the spin of the site at site x by this formula, 2sx plus 1 is nx. So if you're looking at C2, where you have 2 degrees of freedom up and down, that corresponds to spin 1/2. If you're looking at C3, where you have 3 degrees of freedom, that corresponds to spin 1, etc. So then, in each finite volumes, for every finite subset of gamma, you can talk about a local Hilbert space, H lambda, which is just the tensor product of the individual single site Hilbert spaces for x's in lambda. And similarly, the algebra of observables that I will be looking at can also be described as a tensor product of the single site observable algebras, and that is nothing more than the bounded linear operators over H lambda in this context. Okay? Now, frequently, because I will get tired of saying finite subsets of lambda, I will use this notation P naught of gamma to describe the finite subsets of gamma. Not all subsets of gamma, but the finite ones. That's what the naught means here. All right. As Daniel described very well this morning, the notion of observables and support will be important. If you have subsets of gamma that are finite, lambda not contained in lambda, we often identify an observable on the smaller algebra A with an observable on the larger algebra A lambda by just tensoring with the identity in the complement. In that way, we can regard A lambda naught as a subalgebra of A lambda whenever lambda naught is contained in lambda. Similarly, if you look at an observable A on A lambda and you ask what is the support of that observable, well, the support is defined in the following way. We say that it's supported on x in lambda if A can be written as something non-trivial on x, tensor with the identity on the complement. And of course, then the support of that particular observable is the minimal support, minimal set on which the object can be written as something non-trivial tensor the identity. That's our notion of support in this context. And an important part that will come up over and over is if you're looking at two observables A and B and A lambda, and A is supported in X, and B is supported in Y, and X and Y are actually disjoint sets, then their commutator, AB, which is simply AB minus BA, that's 0. That's because of the tensor product structure that we've invoked here. And that's just a statement that observables with spatially disjoint supports commute. All right? Now again, very similarly to what we saw this morning, we will have a local algebra, which is just the union, defined inductively, of the local algebras. That's going to be our algebra of strictly local observables, A gamma loc. And when gamma is infinite and we need to think about a C star structure, we look at A gamma, which is just the norm closure of these local observables, and that I call the C star algebra of quasi-local observables. All right? That's the beginning. Now let's talk about models. Yes?
Sorry, about the commutation thing.
Yes?
Is this a statement that you are the languages of programming?
No, it's not. It's a statement that you have a tensor product structure, and A is the identity outside where B is non-trivial, and when you take the product, you literally get 0 by subtracting.
But if you want to encode like fermionic degrees of freedom,
That would be different, yeah.
commutate, you could do it.
Indeed, yes. But that would be different, indeed. Okay. Let's talk a little bit about models. All right, for us, models will be defined through an interaction, and with the interaction, you also get a dynamics. So we'll describe models with a global quantity that you can look at, of course, in any finite volume that you wish. But an interaction for me is a map phi from the set of finite subsets of gamma into the local algebra, which satisfies two major constraints. First, all the terms are self-adjoint because, again, I want to do quantum mechanics. So I think about all the interaction terms on a set Z being self-adjoint matrices. And the support of those interaction terms, phi of Z, is in the set Z. Otherwise, why would you label it with Z in the first place? So you want self-adjointness, and you want the supports to be contained in the set Z. And that's my conditions on the interaction. Then, given an interaction and a finite volume that you're interested in, you can talk about the local Hamiltonian associated to this global quantity, the interaction. And what is that? Well, h phi lambda is just what you get when you sum all the interaction terms over subsets of lambda. That is going to be my local Hamiltonian. And again, this is a sum over sets. So it's the sum of all subsets of lambda, which luckily, if lambda is finite, is also a finite sum. So this is a finite sum of self-adjoint matrices, so it's still self-adjoint. And the thing to pay attention to is that phi of Z can be regarded in the algebra of AZ, but all of these sets are in lambda, so I don't do that. I regard all of these matrices as being tensored with sufficiently many identities so that they're all in A lambda. And I don't write tensor with the identity because I would never complete a slide if I wrote tensor with the identity as many times as I would need to. So I'm suppressing that. Yes?
So with your definition of interaction, your
So indeed, I think of the global quantity as having absorbed all the boundary conditions that I want. Yeah? I could have appended boundary conditions to the local Hamiltonians in addition, but I'm trying to keep things as simple as possible. Yep. But indeed, the way you should think about it in this particular context is the interaction already knows all the boundary conditions you need to know. Otherwise, you think of it as free boundary conditions, and this is the same thing. Very good. All right, so associated with this self-adjoint operator, you can do functional calculus and look at the Schrodinger evolution, which is e to the minus ith. It's very important in quantum mechanics. And the dynamics, oh, yes?
regarding the definition of interaction and map.
Yeah.
If I have a Hamiltonian supported on site 1 and 2,
Yes?
what does the map take us to if I have it all mapped from site 1?
So I will answer your question, I think, in the next slides where I give some examples. But you are free to choose it as long as you satisfy these constraints. So I believe the answer to your question is that if it's actually on 1 and 2, and that's the literal support, then the Hamiltonian at site 1 would simply be 0, and the Hamiltonian on site 1, 2 would be the non-trivial object that you're looking at. But let me show a few more examples, and we'll get there. What I want to say is that the dynamics that we're looking at here is conjugation by the Schrodinger dynamics. That is called the Heisenberg dynamics. Okay? And when phi is understood, I will stop writing superscripts of phi on both the Hamiltonian and the dynamics. And these dynamics that I'm looking at, these Heisenberg dynamics, they form a one-parameter group of automorphisms of the Hilbert space, of the bounded linear operators, so the algebra. And of course, another thing which will come up often is if I set the time variable t to be 0, then tau lambda 0 of A is just A, it's the identity. Okay? Now, as was asked, let's talk about some examples. First, I'll talk about general examples because these labels come up frequently. So if gamma d is a countable metric space and you pick up an observable algebra, a local algebra, then an interaction phi is said to be finite range if it vanishes whenever the diameter of the set that you're looking at is too large. So finite range interactions are all interactions that have terms supported on sets of diameter less than or equal to r. Otherwise, they're 0. The interaction is said to be non-negative if all the interaction terms are non-negative as matrices. And the interaction is said to be uniformly bounded if, when you soup over the norm of all the interaction terms, what you get is a finite quantity. Right? Now, that's general examples. Let's talk about something more explicit, which possibly may be more interesting or less interesting depending on where you come from. Let's talk about an explicit example. So let's say gamma to be z nu. And at every site of gamma, let's put C2. So at every site, you have 2 degrees of freedom, spin up or spin down. This is called a spin 1/2 system over z nu. And then for every lambda, every finite set, if I take the tensor product, what I'm going to get is C2 to the lambda. So this is a very large system quickly. The system grows exponentially in the size of the sites that you're looking at. Here, mod of lambda is cardinality. If I didn't say that, sorry. That's the cardinality of lambda. Now for a C2 system, there's a very nice basis, the basis of Pauli matrices, sigma x, sigma y, sigma z, and the identity is a basis. And there they are, in case you've forgotten. Now to write down the model that I'm interested in, we need to take these single site objects and embed them into a larger algebra. We do this by tensoring with the identity. So for any finite set, lambda, and any site k, we can look at the alphath spin matrix, so alpha stands for x, y, or z, at site k, which is of course an element of the big algebra, A lambda. And what I get is I just get a tensors of identity, and I put sigma alpha, whichever one I've chosen, in the kth factor here, and that's what this means. Now the explicit example that I'm thinking about is a Heisenberg Hamiltonian. What is that? Well, the interaction that I'm looking at is only non-trivial when z has 2 sites, and those 2 sites are nearest neighbors. Otherwise, it's 0. And if z is 2 integers, okay, this is in z nu, so 2 elements of z nu, and their distance is 1, this is the object that I put down as the interaction term, where jx, jy, and jz are just real parameters of the system for every x, y, and z. And then the Hamiltonian that I'm looking at is, again, the sum over all subsets of lambda of the interaction terms. And therefore, what you're really summing over, because lots of these sets are 0, is those j, k, and lambda for which the distance between j and k is 1 of these interaction terms. That is a typical example you may want to investigate. It's a nearest neighbor, spin 1/2 Heisenberg model. Okay? Now let's talk about Lieb-Robinson bounds. That's why we're here. What are Lieb-Robinson bounds? Well, let's tell you a little bit about them and then tell you more about how you get there. So what is a Lieb-Robinson bound? Well, fix your favorite gamma, which again is just a countable metric space, and an interaction phi on gamma. Pick 2 finite subsets x and y and take them disjoint for convenience sake. Then what? Well, if you let A be an observable on x and B be an observable on x, and you choose a finite volume lambda which contains the union, then as observables in A lambda, of course A and B commute because I said x and y are disjoint, so they're spatially disjoint, they commute. But I can also look at AB as the evolution at time t equals 0. So the Heisenberg evolution at time t equals 0 of that commutator is 0. And one way to think about a Lieb-Robinson bound is, in terms of an analyst's perspective, can you see preservation of this 0 for small times? And the answer is, in many cases, yes. The problem is that for general interactions phi, the support of the dynamically evolved observable A is automatically the whole set lambda whenever t is not equal to 0. That's because there's interactions, and it's non-relativistic, meaning things propagate ultra fast. But What a Lieb-Robinson bound does is show you that if the interactions are sufficiently short range, you can recover this zero property of the commutator by an estimate. And that is what the Lieb-Robinson bound is. For short range models, you can estimate this commutator, again, thinking about this being 0 at 0. You estimate this, and you would like to see it small for small times. And your typical Lieb-Robinson bound has prefactors. That's the cardinality of x, which is the observable you start from. That's a having support x. There's a norm a norm b, a constant, and then something exponential. And the exponential is minus mu. Mu is positive. Sorry, I should have said mu is positive. Minus mu, distance minus v times time in the exponential. So what that tells you is that if times are small compared to the distance over v, this quantity is still small on an exponential scale, right? The first of these inequalities were proven by Lieb-Robinson back in 1972, and that's how the name came into being. In terms of pictures, the way I think about this is, all right, here's gamma. It's not ordered. I don't need a lattice structure here. I just need a countable metric space. I have my set x here and my set y there, and there's some distance between them. Yes? What is v? What is v? V is a good question. V is a constant depending on the interaction. So the interaction of your system, the longer the range is, the larger v is going to be, because v is going to describe the velocity of the system in principle. Yeah? And so you sort of see that here. What I'm trying to sketch here is, first, there's no need to have a lattice structure in these estimates. And second of all, what I'm trying to sketch is a rough idea of what the support of this observable looks like. I'm claiming that the support of this observable is contained in the ball of radius vt about x, because when I take that observable and I commute it with anything outside, by the estimate, this is very, very, very small. It's like it almost commutes. Yes?
Why is it not zero immediately as time?
Because it's a non-relativistic system, and so it immediately has support everywhere. The interactions spread through the entire system automatically. If you don't like that, that's sort of what non-relativistic means. There's no speed of light that bounds propagation. Everything immediately propagates to the boundary. Yeah. Pardon me? I actually have suppressed that on purpose because I'm going to get into it shortly. Range will be defined through an f function in principle, or other things if it's more interesting. So in order to really understand that question, what does short range mean in this context, we express short range through the use of something we call an f function. What is an f function? An f function basically describes properties of the underlying metric space gamma. Gamma needs to have a summable function on it, and gamma needs to have a function on it that satisfies a nice convolution condition in order for the estimates to work in general. We call those functions f functions. Of course, if gamma is finite, you don't need any of this. You can do it, but then the estimates are sort of wonky to interpret. So typically, I like to think about gamma being infinite when I'm applying these inequalities, but that's me. So a non-increasing function, which is strictly positive, that is uniformly summable and satisfies this convolution condition is called an f function. What is a convolution condition? Well, it turns out to be very convenient. If you evaluate the f function at the distance between x and z, and you multiply the f function by the distance between z and y, z is the same, and then you sum out over z, which in some sense is like a discrete convolution, but don't worry about that. You get a prefactor, cf times f of the distance between x and y. That is a very nice property of these functions, and you can ask, do any such functions exist? The answer is yes. In fact, there are often many of them. If f is an f function on gamma d, then you can weight it with an exponential. Actually, you can weight it with lots of different types of exponentials, not pure exponentials with r to the first power. There are other exponentials. Let's not worry about that. There are lots of ways to produce f functions. Exponential rates times an f function is an f function. Those I will call fa. If you're thinking about z nu with a metric on it, it doesn't really matter what metric you choose. Then a good f function is just 1 over 1 plus r to the nu plus 1. I could put nu plus epsilon, but there will be lots of other epsilons, so 1 here is anything positive. This is an integrable function on z nu. And the convolution constant you can estimate in this way, at least that's a naive estimate. And so for any a, if you're looking at z nu d, this is a class of f functions. Note at a equals 0, you get the initial f function that you started with. That is not exponentially decaying at a equals 0. That's polynomially decaying. But for any positive a, this is a class of f functions which exponentially decay. Now, we use the f functions to describe a normal in the interaction. So we use the f functions, these functions which are summable on gamma, to describe how swiftly the interactions decay. In other words, we put a norm on the set of interactions using this f function. So now I'm going to be talking about b of f. There's a set of those interactions phi on gamma d for which this quantity is finite. This quantity is defined by a sup over pairs of points in gamma of this awful sum. But that sup is finite. Okay, what does that sup mean? That sup tells you that, well, if you give me 2 points x and y, and then you create this sum, this is the sum of all finite subsets that contain the 2 points x and y. And what are you summing up? You're summing up the weight or the norm of the interaction terms. So how much interactions are described between the 2 points x and y by this interaction? Well, whatever that is, it's bounded by a constant times the f functions decay between x and y. So in this sense, the norms that we're looking at tell us that the interactions we're considering are bounded from above by the f function between pairs of points. You can think of these as anchored interactions at pairs of points. You can check this quantity defines a norm. So BF is actually a Banach space of interactions. And Z nu D equipped with F is above as before, meaning the polynomial decaying F that we talked about before, which is finite on Z nu. That interactions that are finite range and uniformly bounded satisfy that constant is finite for all A positive. If you're finite range and uniformly bounded, which many of the interactions we consider are, then you're in lots of these interaction classes, not just one.
So the F you gave previously for this
was this one.
Yeah, so this is saying that we're allowing interactions which are on the power law, but like with at least that power.
Indeed, the way to think about it is often you can get things with polynomial bounds, but they are not nice. But if you put the exponential weight, you can see better bounds, and we'll use that to our advantage when necessary. No? Whoops. Okay. This is the Lieb-Robinson bound. I think it doesn't need to be that, but we can talk about that later. Yeah? Okay? All right. Lieb-Robinson bound. So pick an f function on gamma d. Let a be non-negative, and let phi be in BFA. So I'm including the case of a equals 0, so I could be thinking of polynomial decay here. Then there exists numbers c and v phi, depending on a, of course, for which the following estimate holds. What does the estimate say? Well, pick your favorite 2 disjoint sets. Let a be an observable on x and b be an observable on y. We're going to see this a lot. So at some point, I'll stop saying that. The commutator that we're interested in satisfies this explicit estimate. And since the f function has the exponential weight, at least when a is positive, you can bound that from above by this exponential factor. And you see what I had said before. This is the typical form of a Lieb-Robinson bound that you see. The nice thing about this estimate is I can tell you precisely what c, that prefactor, is, and what v phi is, that is this quantity. And then you see from this estimate that, in fact, the left-hand side depends on the finite volume lambda, but the right-hand side does not. The right-hand side depends only on global quantities. So this estimate is actually uniform in the finite volume, and that plays a crucial role in what will come. Now, for a equals 0, if you replace this exponential part with an a in it by 2 norm phi f cf, the estimate still holds with a equals 0, meaning the polynomially decaying case. Some comments. Both c and v phi are independent of the finite volume. I told you that. By the automorphism property, as Daniel said, these automorphisms have norm less than or equal to 1. You can bound the commutator by 2 norm A, norm B. That's true uniformly in time. Sometimes the Lieb-Robinson bound has large values of t, in which case this is much larger than 2, so it's useless. Physically, the Lieb-Robinson bound should only work, or should only be useful at small times, because otherwise the velocity propagates the interaction so that the supports overlap and there's nothing non-trivial to estimate. And you can see that already. Often, if you have overlapping supports, for example, this estimate 2 norm A, norm B is better than what you would get out of the Lieb-Robinson bound, so you shouldn't use it. Again, there's still a bound if x is not, and y are not empty, but the above is usually better. For the experts in the audience, you can replace the minimum cardinality of the sets x and y with minimum boundaries, but that goes beyond the context here of what I want to talk about. And in the case that phi is uniformly bounded in finite range, or in some other class where you know that it's in this class of interactions for a in some interval. So you have a positive interval, you have an interval of positive a values where this thing is in the Banach space. Often people take the v-phi's, the velocities that you get, and optimize over a. And that optimal value is typically referred to as the Lieb-Robinson velocity. But even in that case where you've done some optimizing, the fact that you call it a velocity isn't the statement that there are observables that the dynamics propagates at that velocity. That is a misnomer that some people have. It's not true. You can do that in some cases, but not all. But in any case, whether you've optimized or not, the v-phi that you get is always an upper bound on the propagation of information in the system. Some words on the proof. Where am I at? Here I am. Good. All right. So as many good theorems go, this theorem is the result of a well-chosen lemma. And the lemma that we have is called norm preservation. It's sort of a silly lemma, but it's ridiculously useful when you need it. The lemma goes back to differential equations. And it says, suppose you're trying to solve a first-order differential equation of a certain type. Can you do it? Often the answer is yes, because it's first order. And then the answer is, if you can do it, can you estimate the norm of the solution? And the answer to the norm preservation lemma is, if you're trying to solve a differential equation of this form, initial value problem, that is b of h valued. So the function f has domain on the real line, and it's valued in the bounded linear operators over the Hilbert space. The differential equation is this type. The norm on the solution can be estimated as follows. And what should you see in this estimate? What you should see is that the estimate doesn't depend on the first term, corresponding to c. So this is a silly lemma that says the solution of this differential equation can be estimated. Great. But the point of it is that the first term in the differential equation doesn't contribute to the estimate, and that's because the first term preserves norm. And since it preserves norm, you can write it as an explicit unitary, and in the estimate, you can bound it by 1. And that's literally what we do. Look at the quantity c that's in the first term of the differential equation. Corresponding to that c, what were the assumptions on c? C is continuous, great, and it's pointwise self-adjoint. So it's self-adjoint for every value of t, satisfies this. Then what? Well, you can then construct from that continuous function what I call a Dyson series. That is a sum, it's actually a series, of iterated integrals of c, taken in the appropriate order. This is well known if you know it. It's not well known if you don't know it. But there's this problem-solving session, and I ask you to look at some of these properties later. Turns out, because c is self-adjoint and continuous, this is unitary for every t. It's called the Dyson series. And if you set d equal to 0 and you just look at the first part of the differential equation, you can explicitly write down the solution of this differential equation in terms of that u. And since u is unitary, it preserves norm. The norm does not change at all. Yes? So I'm going to find a dimensional space, and I'm evoking that as much as possible. I don't want to talk about topology. All norms are equivalent on finite dimensional space, so it's norm continuous. Otherwise, I would be saying strongly. Yes? Good. Now, the nice thing about differential equations, I think they're nice, is that once you know a simple thing, you can often find more complicated formulas. Variation of parameters is the cheapest trick in the book to allow you to solve more complicated differential equations once you know some part of the solution. And in fact, you can use variation of parameters to find the function f, which solves the full differential equation, because you know the solution to the first part in terms of u. So assuming that that's correct, this is now an explicit expression for the solution of the differential equation, and if you norm bound it, you get the norm preservation lemma, as I claimed, because these are all unitaries. And again, I didn't say anything about uniqueness, but if you know a little bit about differential equations, you can prove uniqueness for both f and g from a Grandwall lemma. And if you don't know what a Grandwall lemma, that's okay. It's going to be in the problem session. You can talk about it. All right? But this is the norm preservation lemma. It tells you that if some portion of your differential equation can be absorbed with unitaries, take advantage of it. It won't contribute to the growth of solutions. Now let's use that to prove our Lieb-Robinson bound. Let's use that to prove our Lieb-Robinson bound. Let's create a function from the real line into the observable algebra. That is the object that we want to look at. How do I estimate the norm of this commutator? That's what f is. Well, if you play around with it a little bit, this Heisenberg dynamics is very explicit. You can calculate the derivative. The derivative of the Heisenberg dynamics is I times tau t of the commutator of h lambda with a. H is what generates the dynamics, and therefore the derivative is in terms of commutators with the generator, which is h lambda. Now, h lambda is what? It's a sum of a whole bunch of terms of the interaction. But it's commuted with a, and a has explicit support. A has support in x. So as you sum over all these z's, all these interaction terms, only those that hit the support of a will survive. The rest will be 0 because the commutator is going to be 0 if they have disjoint supports. So I can restrict my attention just to those sets that intersect x. That's the first observation. And then, of course, this is the main term you get when you differentiate that function I started with. You get this. Then that commutator is a nice object. You put the automorphism inside. The automorphism hits h lambda tilde. It hits a. It produces this. And then you Jacobiize. So you turn something that looks very simple into two complicated looking terms using the Jacobi identity. It just says if you cycle through commutators, eventually you get 0. And hopefully I didn't screw it up. This is what I get. But what do I see? F was tau t lambda a b, the commutator. And that appeared in the first term that I've got here. In other words, up to having complicated definitions of what C and D are, I'm in a situation where I can apply the norm preservation lemma. And so I do it. The object I'm interested in F is this thing in norm. It's bounded from above by f at 0, which is this guy, plus the integral of this thing. I estimated a bit. I took 2 norm this thing, which is a, times that thing, and put it in there. And that is what I'm integrating. Then if I sum out what's left of the interaction terms, it's those sums z in lambda such that z hits x. That's what contributes here. And I see something I like very much. I see I have an inequality where the object on the left-hand side reappears in some sense on the right-hand side. In other words, I can iterate. I can iterate this inequality by saying, OK, I had this estimate here. So when I reach this object, I use the same estimate that I had for this guy with now t equal s and a equals norm phi, or phi of x, phi of z. And I go. And because I'm brave, I can do it all the way to infinity. And you can see that this works. What do you get? Well, you get a series. The 0th term is gone because a and b commute. So there is no 0th term. N equals 0 is gone. I start with n equals 1 here. And then I get some contributions in a sub n. These contributions come from integrating a symplectic integral. If you've done this, this is the answer when you integrate 1. If you haven't, again, it's in the problem section. So there's all sorts of interesting things you can look at. But the ANs are the interesting things. The ANs are the weights. And in estimating this, you need to control the weights as best as possible. How do you think about these weights? Well, the ANs represent an interaction weight associated to sums over intersecting sets which start at x and end at y. I call them chains. So there's sums over sets which must all intersect, and the first one has to hit x, and the last one has to hit y. And then you need to sum up all those sets and calculate the norm of the interaction. So let's look at a couple. Once you've done the first 2, you know how to do the rest. Let's look at the first one. What's the first one? The first one says, suppose you're in a situation where you have one set that connects x and y. How can you estimate that? Well, sum all sites in x, sum all sites in y, and sum all z's that hit those sites. This is an overbound. And actually, that's literally the norm we put on the interactions. So we get this estimate very simply in that case. What about if there's 2? If there's 2, then you sum on all sites in x, you sum on all sites in y, you sum on all possible sites in forever. And you let the first set hit x and z, and the second set hit z and y. The second set hits y. The first set has to hit x, and they have to intersect. And I don't care where they intersect. They can intersect anywhere. And so I summed on all possible z's where they could possibly intersect. But then I'm in great shape. Again, I can estimate this with my norm. I can estimate this with my norm. And that gets rid of the sum over sets. The only thing that's left is the annoying sum on z, but that's where the convolution condition for the f function comes in. You can sum on that diagonal, and you get a constant, but that's at the estimate. And once you've done it once and twice, you can do it n times at the blink of an eye. That's the estimate. So the estimate then follows. Plug in what you got. realize that this is almost an exponential minus the first term, so I write down the exponential minus the first term, and that is the Lieb-Robinson bound. This part, in the event that there's an exponential weight, you can estimate it, the exponential weight out. You sum out on one of the terms, you get the integral of f, and the other one produces a cardinality of the set. Sum on whichever one is bigger, so that you get the smaller one in your estimate. That's why we get the minimum. That's this. And if a is 0, and it's not exponential, then you just get what you get. And that's the end of the day. That is the estimate. Now, what's much more important is that we are able to go through some applications of these estimates. All right, so I want to go through 2. Now, in future lectures, I will often stop referring to this as a Lieb-Robinson bound and start referring to it as a quasi-locality estimate. It's an estimate on the dynamics which describes to you how well you can approximate this dynamical evolution with local objects. I'm going to explain why I say that with this application, because if you satisfy a Lieb-Robinson bound, you satisfy these strictly local approximations, and that's what I want to convince you of. But later, things are going to go beyond the context of what Lieb and Robinson could do, look at many other different contexts, and so I'll start talking about these as general quasi-locality estimates for a given dynamics of some form. Okay? And that all goes back to this application. So suppose I have one of these dynamics. I know a Lieb-Robinson bound for it, and I want to see what good did that give me? Did I learn anything from proving this Lieb-Robinson bound? And the answer is yes. You can approximate that dynamics with a strictly local object and estimate the approximation rather well. What does that look like? Well, let's talk about normalized partial traces, which some people know about and others don't, but that's okay. What is a normalized partial trace? Well, take your 2 favorite finite dimensional Hilbert spaces. First, you don't need finite dimensional to define this. But again, that's what I'm looking at. Second, they don't need to be Hilbert spaces. All you need is vector spaces. But again, I'm being pragmatic. I'm looking at Hilbert space theory. I'm looking at quantum spin systems, so I'm taking advantage of finite dimensional and Hilbert space structure. And I'm going to define the normalized partial trace as a mapping from the bounded linear operators over the tensor product of the 2 Hilbert spaces I'm looking at. And that is a map which goes from the bounded linear operators over the tensor product to the bounded linear operators over the first factor. And what does it do? Well, it eliminates the second factor, in principle. The map is the map that takes products AB into the product A. So in words, you've traced out the degree of freedom associated to the second Hilbert space. That is what the partial trace does. Since you can find a basis here of objects of this type, this specifies the map entirely. Because, of course, it's linear. Sorry, I don't say this enough. My maps are all linear. I apologize. My maps are always, always, always linear. So a linear map can be specified on a basis. And I'm using that. Yeah?
Are you here picking B to be trace 1, or?
I'm doing the normalized partial trace. So indeed, since B is finite dimensional, I can normalize. No, I'm dividing by a constant in the traditional notation. This is the normalized partial trace, not the partial trace. So I have done that. Here I am using that B comes from a finite dimensional Hilbert space. Yeah? Okay. Again, normalized here means that I'm getting, when I stick in the identity for A, I get the identity out. If the word normalized is gone, typically what you get is trace of the second Hilbert space as a factor here. I have subsumed that as a constant in my map. Now, what I said was this partial trace is tracing out the degrees of freedom associated to the second Hilbert space. You can see that in a different way. You can check that this partial trace may also be described as integration with respect to Haar measure. You look at the Haar measure defined on the second, with respect to the second Hilbert space on those unitary group. Again, I'm finite dimensional, so all of this makes sense. And you simply integrate out unitaries over the second factor of the Hilbert space. If you check on a basis, this map and that map agree, and therefore they are the same. Yes? D mu H2 is the normalized Haar measure on the unitary group. Yes. Yes. So, and again, the Hilbert space structure is not necessary here. Yes. Yes. So I am normalizing this thing in a specific way. That's correct. Yes. All right.
I think what the identity, or the trace of B normalized divided by the dimension of H1.
All right.
The trace of B should be there.
Indeed. All right. So, okay. Fair enough. The trace of B should be there. There should be a constant factor. Indeed.
So if the trace of B is 0, then what happens?
Mm-hmm.
So if the trace of B is 0,
If the trace of B is 0, you're looking at a very interesting space, right? So there's nothing in it, right? Because if there's a nice vector in there, you can define an orthogonal projection onto that vector. You get trace 1, at least. Yeah. So trace will not be 0 in these cases. All right. Fair enough. Fair enough. I was trying to get rid of extra constants. In any case, if you then want to estimate strictly local approximations, look at the take an f function on gamma d, and take an interaction that is in the Banach space for the exponentially weighted space. Then if x is a finite set, for any n bigger than or equal to 1, it's convenient to inflate that set, and we call it x sub n. That's the sum of all y in gamma, such that the distance between y and x is less than or equal to n. So you start with a set x, and you inflate it by n. You add the sites in units from the boundary of x. Yeah? All right, then what? Well, take an observable A in the algebra at x. So A is initially supported at x. Let T be in R. And suppose you're in a volume lambda that contains the inflation of x out to n. Then ask yourself a question. What is the difference between the dynamics and the partial trace of the dynamics? Now, the partial trace of the dynamics that I'm taking is by looking at the Hilbert space on level lambda and writing it as a factor, where the first factor is h restricted to x of n, and the second factor is the complement. Well, that defines for me the partial trace. I can write that in terms of the integration over Haar measure. And what I see when I look at this is that I get an integral of the commutator. And these u's are supported on the second Hilbert space, which has some distance from the support of A, which is x. It has, in fact, distance n from x. And so I can estimate how badly this approximates the dynamics, or how good the approximation is, by taking the norm of this integral. If I take the norm underneath, I get the norm of the commutator. A is supported on x. U is supported n units away from x. If there's an exponential weight here, I get this estimate. The nice thing about this estimate, again, is it's uniform in lambda. It doesn't depend on lambda because it's just these commutators. And so the finite volume dynamics can be approximated by a strictly local observable in here with an estimate that is uniform in lambda and exponentially decaying in n. Yes? So you can do that, but I don't know what the estimate would be if you do it. It depends on what you were looking at, right? You have to look at something concrete in order to do this. I'm using very much that I know a lot about this particular object, right? So you don't need exponentially decaying here. A similar decay bound holds even in the case of a equals 0. Yeah? It's just not exponential. It's whatever the decay of the interaction is. If it's polynomial, you get a polynomially decaying bound. Right? That's the first estimate. The second estimate or application that I want to talk about is the existence of the dynamics in the thermodynamic limit. And that looks like this. So another use of quasi-locality estimates. Again, these are quasi-locality estimates that are uniform in the finite volume. So if you have a quasi-locality estimate, so a commutator estimate of Lieb-Robinson type, and the right-hand side of your inequality is uniform in the volume, then you have a good chance of being able to prove that there's a limiting dynamics for the object you're looking at. And that's, in fact, a theorem. Let f be an f function on gamma d. Take phi in the Banach space of interactions that decay like f. Then there exists a strongly continuous one-parameter group of automorphisms of the full C-star algebra, A gamma, quasi-local algebra. And that infinite volume dynamics is the limit of finite volume dynamics. Now, this limit exists along any non-decreasing exhaustive sequence of finite subsets, meaning the sequence of sets increase, Exhaustive, or sometimes absorbing, means that for every x in gamma, there is an n at which that x is in lambda n. So it eventually contains everything in gamma. But the limit is actually independent of the choice of finite sets that you choose, as long as you make them in this manner. And the convergence is uniform for T in compact sets. Yeah? What about the what? The rate. You will see that. Yeah? But what I say is the convergence is uniform for T in compact sets. It depends on the f function. You get decay, which can be expressed in terms of the tail integral of the f function. So depending on how fast your f function decays, you can describe explicitly the rate of decay that you get here. Yeah? All right. So how do you prove this? Well, again, I include the proof because this is something that works quite generally whenever you have an interaction, whenever you have a dynamics with a quasi-locality estimate, or an estimate of Lieb-Robinson type. So how do you prove it? Fix your favorite observable that's local, and a time t. Now let lambda n be one of these increasing, absorbing, or exhaustive sequences. Let x denote the support of A, and take m large enough so that x is in lambda m. Since they're increasing, it's in all subsequent sets. Let lambda n be the bigger set, and lambda m be the smaller set. Look at the evolution on the big set minus the evolution on the smaller set, and see what you get. Well, this difference can be written as an integral of a derivative. It's easy to check. If you integrate this derivative, what happens? Well, if you open this up, you evaluate this thing at t, then this is 0, which is the identity. You get the evolution on a large volume, which is there. And at 0, which is the bottom part of the integral, you plug in, that's gone, you get t, that's the evolution there. So it's easy to see that this is an integral of this derivative. Now, since you know what the generator of these dynamics are, you can take this derivative and calculate it and see what it is. It's the commutator of the difference of the Hamiltonians. H lambda n on a big volume, H lambda m on a smaller volume. This difference only contains certain type of interaction terms. In fact, any interaction term phi of z in here, where z is in lambda m, that's going to cancel. In fact, since this dynamics is totally in lambda m, any interaction term z here that is totally in lambda n and not in lambda m, it's also going to vanish. The only terms that contribute here are those terms z that intersect the boundary and also go into lambda m, but I don't need that for the estimate. Many of the terms cancel. That's what you see here from this derivative calculation. And therefore, you can estimate this difference by a sum over sets of integrals of excuse me, Lieb-Robinson type commutators. So using essentially a Lieb-Robinson bound, you can estimate this, and you get this bound. What do you see in this bound? You see a constant. You see time factors, which again, time is fixed in this estimate. I'm fixing time and going to infinity. And then you have a sum over sites in x, and f functions being summed over z's that eventually get farther and farther and farther away from x because you're summing over the elements of the boundary of this exhaustive sequence, which is going out to all of gamma. This is the tail of a uniformly summable function. Hence, it goes to 0. Since there's only finitely many points in x, this quantity goes to 0. It goes to 0 at a rate of the tail sum of f, which you can estimate if you would like. The cardinality factors of x, norm of a, et cetera there, and time factors here. But this is how you prove that you actually have an estimate on the Cauchy sequences. In fact, you have an estimate on the Cauchy sequences that is uniform for time in compact sets. And you can use this to show using what Daniel introduced this morning, I would call the BLT theorem, that once you have estimates on the local algebra, there's automatically a unique extinction to the full C-star algebra. Okay. Another nice thing, which I'll only state in, briefly, is that since I have norm convergence, since in the finite volume I had Lieb-Robinson bounds which were uniform in the volume, as I take the limit as n goes to infinity, the limiting dynamics is also quasi-local in that it satisfies the same Lieb-Robinson bound that you had in finite volume by just taking the lim sup of both sides of the argument, because I have norm convergence here. So not only do you have a nice limiting dynamics that is a one-parameter group of C-star algebra of automorphisms, star automorphisms, they also are quasi-local. They satisfy the same finite volume Lieb-Robinson bound that the limiting ones did. Okay. Now, This is basically my conclusion. We have discussed a basic Lieb-Robinson bound. We will investigate other quasi-locality bounds and further applications in later lectures. Thank you for your attention, but there's actually one more slide hidden behind it. So what I want to talk about is what I didn't talk about, because I think that's also interesting. So these estimates are incredibly useful. They've come up in lots of different ways, and they will come up in lots of different ways in other talks at this conference. So there's a brief list here that I've included of models where locality estimates have not only been proven, but been proven useful in doing applications. So you have quasi-locality estimates for lattice fermions. You have quasi-locality estimates which are coming into existence now for fermions in the continuum, so real continuum models, where you have quasi-locality estimates. You can look at general lattice models, which don't have finite dimensional Hilbert spaces at every site. These are models where the Hilbert space at every site is infinite dimensional. There are models, for example, of oscillators or even anharmonic systems. There are models of unbounded on-sites and bounded interactions, like rotor models, for which you have quasi-locality estimates. There are models of open quantum systems, which I think people are going to be talking about later in the class, in the lectures, where people have proven and used locality estimates. There are different classes of locality estimates called long-range Lieb-Robinson bounds, which have a different flavor, and they may come up later in the talks. And something that I like very much is there's a way to describe many-body localization for random quantum spin systems, and you can describe it also in terms of these locality estimates. So that's just a flavor of things that could come, but let me stop here with saying thank you for your attention. Excuse me.
So thank you very much. Are there questions? Yeah. So what there?
Up there.
Who had a question?
Someone else. Let's say you're in a situation where you have an interaction, but you don't know an f function such that the interaction is bounded with respect to that f function. Is there something I can do besides guessing and checking to find an f function?
So if you're looking at an integrable system, you have hope. Yeah. So if you know formulas for the dynamics, right, then you may not need the structure of the lattice. You might just be able to use your bare hands and do it. That's happened in a couple of examples. Yeah. Let me reframe your question in something you didn't ask. If you're looking at a gamma that doesn't have an f function on it, like a really crazy tree, for which I don't know that there are f functions, yeah, then I don't know what to do. I don't. Yeah. But if you're in a space where there is an f function on gamma, you just don't have a bound on it on your interaction, then I would say, depending on how nice it is, maybe there is hope, because at least there's underlying f functions in your space. You can approximate in lots of different ways the f function, the interactions, and hopefully prove something. But if you're on a space where there isn't an obvious f function around, then these arguments are not cooked up to handle such a situation. So you would have to go on your own. Yeah. Okay.
For your theorem on the thermodynamic limit, maybe 2 slides back, is I think it was this one, yeah. So is there a relationship? Daniel at the end of his lecture explained how if I wanted to define an automorphism on the quasi-local algebra, I could just define it on the finite subalgebras. Is there a relationship between this result and that what Daniel was presenting? You have these tau t of lambda n, so these are.
So likely the answer is yes. I just don't look at it that way. These are all dynamics that I've constructed in a very explicit form through the Heisenberg evolution. It's not of the type per se that Daniel was looking at. I think likely the answer to that is yes, there are good relations, but I haven't really pursued them. Yeah. Sure.
You could look at this limit.
You could look at this limit up here, and this limit is for all A in the local algebra.
Mm-hmm.
And so that tells you how tau gamma t of AX for the local algebra. And then you know already that this extends to the quasi-local algebra. And this limit also works, I think, for all elements in the quasi-local algebra.
To further make the connection, you can show that you can approximate any of these things by a finite depth quantum circuit, as was described before.
Right. Good.
Any other question?
Peter.
Oh yeah.
Can you say something about the converse? So suppose I have some one-parameter group of automorphisms satisfying a Lieb-Robinson type of bound. Can I always find dynamics that generate this one-parameter group? Local dynamics?
I think there are people that have looked into this, but I don't have a general answer to that question, no. Do you know? Yes?
The answer is no.
Okay, that would...
That's
Take, for example,
Yes.
in one dimension translation.
right. Yeah, of course. Yeah.
Oh, indeed, yes,
Yeah,
right.
yeah.
Mhm.
Yeah, of course. Yeah.
One you can always find an interaction.
Oh,
So further question?
she asked for the answer.
you- yeah, that's.
No.
That's good.
Short and precise.
That's
yeah.
correct. That's correct.
Any other questions? Yeah.
Thanks. You mentioned that just because you can do this optimization thing and define a Lieb-Robinson velocity for a given interaction, but that doesn't necessarily mean that there are degrees of freedom propagating at that speed.
That's correct.
Could you say a bit more about that? Like some example you have in mind?
So in certain simple systems like the XY model, you can create observables that propagate at, I think, exactly the velocity that the Lieb-Robinson bound produces. Those are some of the only models I know for which you can find observables that propagate at explicit velocities like the Lieb-Robinson velocity. So if you look at classical systems for which you can also make sense of Lieb-Robinson bounds, you can look at the totem model, not the quantum totem model, but the classical totem model. We also have some results where we can find observables that propagate at almost the Lieb-Robinson velocity, but not exactly. In the XY model, I think you get exactly there. But that all the velocities, all the estimates that you get, the prefactors there, they're all upper bounds. You cannot propagate faster than that, and the estimates basically show that. Go ahead. A second comment, which just came to my mind. There are interesting systems, for example, random systems that have disorder, for which the Lieb-Robinson bound that you get is positive, and the actual velocity can be shown to be 0. So you get all sorts of different phenomena.
That answered my question.
Okay, sorry. Yes, indeed.
On the topic of optimization, I had a naive question. How does one go about optimizing these bounds? Is it just trial and error, like hoping that you find, like how do you know like some bound is optimal in a sense?
So let me tell you something uninteresting, which I know. Here, you see this? If you get your hands dirty, most interactions you can put a pretty precise function of A to estimate this. You also have pretty good control over this. And if you look at there's a singularity, so for the A, you have some hump. Frequently there's a minimum. That's all I'm talking about, right? So that is the minimum, or the optimization. It is not sophisticated in the slightest. It's this thing, yeah?
Thank you.
Yeah.
Any other questions? Yeah.
I had a quick question about the formulation of the partial trace in terms of the Haar integration.
Yeah.
Is there like a nice intuition to sort of see that? I've never seen that formulation before.
So verbally, yes. Verbally, the partial trace is simply integrating out the degrees of freedom. Whether you do it by definition with expansion and a basis, which is the way it's typically defined in finite dimensional cases, or you integrate over these unitaries corresponding to Haar measure, you're doing the same thing. You're integrating out the degrees of freedom associated to the second Hilbert space. That's the best answer I could give you for motivation for this. And then you have two linear maps. You can check that they're actually equal. Yeah, so that's it.
Okay. So it seems there are no more questions. Then let's thank the speaker again. And we will resume after the break, which is in 10 minutes. Yeah.
Sorry, Sven.